today I want to look at I think the best section of the unit, the most fun section, as we get to solve some problems, some applications involving linear systems. And finally, we get to a point where, we're just starting to get to a point in math where we can do some things that are, sort of real. You get to calculus, you're all the way there, but we're starting to get to where we can do some interesting things. So what about something like this? So get those things all the way closed. You got to really focus on this. So first of all, let me preface this by saying, we've left the days in math where we have sort of a magic formula that's always going to work. That's no longer the case. Every situation, when you look at these applications, they're all going to be different. There's a set of just overriding principles that are going to work in general, but you have to look at each problem differently, and you have to be creative. So we've got the situation here. Soybean meal is 14% protein. Cornmeal is 7% protein. How many pounds of each should be mixed together in order to get a 280-pound mixture that is 13% protein? Okay, so what are we going to do here? We've got to, in general, the steps we need to take are, and this is really important, this first one, define your variables and write them down. You don't want to have your thinking derailed by always having to stop and remember what the variables represent. So write them down so it's right in front of you. You can always just look at it and it reminds you very quickly. So you can be focusing more on concepts and relationships than having to remember details. So that's step one. Define your variables and write them down. Step two, we need to set up our equations. And remember, the fundamental theorem of algebra tells us we need to have at least as many equations as there are variables. And then step three is we just flip into algebra mode and solve the system. Okay, well, define your variables. Now, the variables are almost always going to be the things that are being asked about, the unknowns. If the question doesn't ask about something that's unknown, it's a pretty trivial question. The information's just given to you and you move on. So, can anybody tell me here, what would the variables be? What about it though? The price of the cornmeal? How many pounds? Yeah. And look, there it is right there. How many pounds? So that's, when they ask the question, that's keying in that those are the variables. Let's get rid of earbuds, please. Those shouldn't be out. So how many pounds of each should be mixed together? So we got pounds of soybean meal and pounds of cornmeal, I guess, right? Okay, give me thumbs. Does that make sense? Those are the unknowns. Okay, so let's define those and write them down. Now, how many equations do we need here? Yeah, we need two. Okay. Okay, can anybody find an equation? And they must come from some information that's given to us, right? So you kind of look at numbers a little bit on this stuff sometimes. Anybody see an equation? Keep in mind, X is the number of pounds of soy meal. Y is the number of pounds of cornmeal. So there's one pretty obvious equation there that's staring you in the face. Anybody see it? Yeah, good. Okay, you always look for an X plus Y equals equation, right? You always look for a sum of the variables if it's there, because that's the easy one. That's kind of the low-hanging fruit. What does X plus Y have to equal? 280, yeah, right? Everybody see that? We have a total of 280 pounds of our mixture of those two kinds of meal. And so there's one equation we've got to make. Okay, so what's that equation going to look like then? You essentially told me, but what's the first equation going to be? Yeah, good. X plus Y equals 280. Good. Okay, one down, one to go. What's the other one probably involving? Okay, the percent of the protein, yeah. So now how am I going to get that one? That one's a little trickier. Wants to know how many pounds should be mixed together in order to get 280-pound mixture, sure, of, they specify they want it to be 13% protein. What do you think, Tanner?
You can do 0.14x plus 0.07y equals 280 of 0.13.
Okay, so 0.13 times 280. Yeah, that's excellent. Okay, now let's talk about that. That's very good. What's your thinking there? What does 0.13 times 280 mean? Okay, that's 13% of 280, isn't it, right? If I want to find a percentage of something, I'm going to multiply by the decimal version of that percentage, right? When we say percentage of, we're just multiplying. Okay, so yeah, that's going to tell us, what percentage of that 280-pound mixture is protein. What does the 0.14x represent then? Not the percent of protein. I mean, I get it, 14 is the percent, but that product of 0.14 times x, what does that represent? I mean, you're so close. I understand why people would say it's a percentage. It's the amount of protein that's coming from the soy meal, right? Because 14% of the total soy meal is protein. So this first term right here, this actually represents the amount of protein from the soy meal measured in pounds, right? 14% of those X pounds is protein. Okay, and then of course 0.07y is what? Yeah, the amount of protein that's coming from that 7% of the cornmeal, right? Make sense? And that has to add up to the total amount of protein, which is 13% of our total mixture. Okay, give me thumbs on that. Does that make sense? Okay, once we get there, this is a piece of cake, right? Now we've got a linear system. You're getting really good at solving linear systems. So solve it real quick. Jump in your Chromebooks and solve that. Any way you want. Would have looked like this. Right, everybody agree? We're just going to set up matrix A that looks just like that. Looks like our system. And then RREF it, and we got it. There's the matrix way. Anybody use a graph? Sure, we could use a graph. If we use a graph, it's, we got to zoom out a bit, right? Because we can't see anything, but we just have to zoom out until we can see an intersection. And that's really all we need, right? Once we see the intersection, there it is. And you notice when you click on the intersection, it gives you that little button that just drops the intersection as a point into your list of things that you're graphing, which is kind of nice. Then you can click label, and it even puts a point there. Okay. So let me take a picture of that. Okay, so for your notes, there it is. All right, click those or close at least part way, and let's talk about another one. How about something like this, a little different look. So the Rolling Fund Bike Shop estimates it will need to purchase $6,500 of new equipment to manufacture doggy sidecars for bikes. The cost of building each sidecar will be $250, and the revenue from each sidecar will be $550. Okay, well, first of all, let's talk about some vocab here, because this is kind of some economic stuff, right? What's revenue? Okay, income. Yeah, that's the amount of money that's coming into your company. What are costs? Okay, that's the money that's going out, right? That you're paying to produce, well, your sidecars in this case, right? What's profit? So what's that mean? Give me an equation. Profit equals what minus what? So revenue minus cost. Yeah, that's profit. Okay, revenue minus cost. Okay, so we want to come up with a function that predicts that, well, first of all, what are our variables going to be here? I mean, is there, I guess this is a little different, right? We really only have one variable, which is the number of sidecars we're producing. Does that make sense? We don't really have, I mean, so this is a little bit of a different problem. In fact, you could argue this isn't really even a systems problem, but we could look at it that way. So what's the function that predicts the revenue? So we call this the revenue function in terms of the number of sidecars that we sell. So if I sell X sidecars, what's my revenue going to be? How much money's coming in? Okay, so it says the revenue from each sidecar is $550, so that's how much we're charging. So if I'm selling X of those, what's my revenue? Yeah, 550X. Okay, so we got a revenue function. Oh, and that is, where's that? I guess we have to write that one down. Okay, so the revenue function. I guess we have to write that one down. So the revenue function is, we'll call it R of X, 550X. So what's the cost function? Okay, so the cost of building each one is 250. So we call that the incremental cost, right? Because it's associated with each sidecar that we build and sell. So what's the incremental cost going to be? 250, what's Y? Okay, but we already defined that number of sidecars as X. So yes, actually just going to be 250X. Is that it for the cost? Okay, there's also a fixed cost, right? We have this one-time cost of $6,500 for equipment. So what's our cost function going to look like then? Yeah, okay, cost function is going to equal, it doesn't matter the order in which you write these, we've got our incremental cost of 250 times X plus our startup costs or our initial costs of 6,500. Okay, so now the question is, we've got those two functions now, a revenue function and a cost function. How many sidecars will the shop need to sell to break even on this venture? How could I find out? Yeah, set them equal to each other, right? That's really all I'm doing. And if I wanted to, a graph is pretty useful here. If I wanted to graph both of these functions, right, I've got my instead of Y, I'm going to call that R of X. So that's my revenue function that I can graph. There it is. I'm going to call this C of X. There's my cost function. And where do they break even? Well, right there, right? That's when the revenue catches up to the cost. The cost function starts off, obviously the cost function is higher, the values are higher than the revenue function initially because we had to pay all that money for startup costs, right, for my initial costs. So it looks like, how are we going to interpret this? They want to know how many sidecars will the shop need to sell to break even? Okay, so you guys interpret that for me. How many sidecars would we need to sell? Everybody see that? 22, right? How come it's not 21 and 2/3? Yeah, you can't sell 2/3 of a sidecar. Would 21 be enough? No, 21 is not quite enough, right? So it'd have to be the next increment up from 21 point whatever that is. So it'd be 22. Okay? Make sense? And we can see that's when we're profitable, would be in that region there. And that's when we're not. That's when we're losing money up until that point. Okay? All right. Okay, and you've seen, I think, lots of problems like that in the past. Okay, why don't you go to the boards and try one of these. Try this one. Variables are what? Okay, and what would the units, it's good to kind of give me units on the variables. Liters of 6%, so liters of that strong acid, and then liters of 2%. Okay, so equations. Do we have a sum of an easy sum of the variables equals equation? Okay, good. The total, we need a total of 80 liters. So x plus y equals 80. And then what's the other equation that's coming from the percentages? Okay, yeah, and explain that. What does, for example, what does 0.05 times 80 mean? So, okay, so 5% of that 80 liters is what? Okay, it's pure acid, right? And then it's diluted to a 5% solution. And so then the 0.06x represents the total amount of acid that's coming from the strong solution plus the total amount of acid coming from the weak solution equals the total amount of acid, right? And then you just solve that. How many people used a matrix? It's a little quicker, isn't it? Once you get going on it. So, and the beauty of that also is it's going to be able to give you back like fractions. You know, like if you use the graph, you're stuck with decimals, but this will give, you can turn these into fractional answers when you use the matrix. So, and we got what, 60 and 20? 60 liters of the strong and 20 liters of the weak solutions. Okay, good. All right. How about one like that? Take a look at that one. See if you can wrap your brain around that one and tell me what to do. So I'll read it in case you're in the back and you're having a hard time reading all that. The theater sells 3 types of tickets: general admission, senior tickets, and child tickets. Mark bought 9 of the general, 2 of the senior, 3 of the child tickets, and he paid $170. Sarah bought 5 general admission, 4 senior, and 7 child tickets and paid $173. Kyle bought 4 of the general admission, 1 senior, and 6 child tickets and paid $116.50. Find the cost of each type of ticket. Okay, so what are the unknowns? Like how many unknowns are we going to have? Show me with your fingers. 3, okay, I agree. What's the first one? Okay, cost of a general admission ticket, good. Next one? Cost of a senior ticket, and then finally, cost of a child ticket. Okay, good. What about equations? Can we come up with some equations here? Now this time, do we have one of those simple sum of the variables equals one? Say it again. Good. Okay, so we need 3 equations total. Good. Do we have one of those x plus y plus z equals equations here? Oh, good. Okay, we don't really have one of the easy ones, but where's our first equation? Where's that going to come from? Okay, good. That's going to come from Mark. Oh, what happened here? Yeah. Okay. Yeah, so the first one comes from Mark. And what would that equation be? Kyrell, you were telling me? There we go. Okay, good. So we get 9x plus 2y plus 3z equals 170. What about Sarah then? What's hers going to be? There you go. Good. And then following the same logic, Kyle's purchases give us that equation. And so then we would just solve that system how? Graphing? Using a matrix. We can't graph, right? So now we're stuck. We just have to use a matrix calculator. And anybody do it yet? What'd you get?
X equals 13.5, y equals 11.5.
Okay, so X was 1350, Y was, and Z was, all right. I'll buy it. Looks good. Okay, give me thumbs. How we doing? Good? All right. Okay, this one's a little tougher. I think it's a little tougher. Go. Probably want to bust out those notebooks so you can maybe write down the variables here. How many variables did you get? 3. Okay, what are they? What are the variables though? Like what's X? Okay, here's the question. How many units of each mix? Units of mix A. Okay. Oh, where'd that go? Huh. I thought maybe I didn't write those down. Oh, well, that's all right. I gotta do some writing, darn it. Okay, so X units of mix A, Y units of mix B, Z units of mix C. Okay. All right, so we need some equations here. This time, do we have an X plus Y plus Z equals? We don't, do we? Doesn't tell us how many total units. Anybody have any idea where we're going to get the equations from? Okay, how are you going to use protein here? Okay, so we need a total of 27 grams of protein. How much protein is coming out, somebody real quick, how much protein is coming out of mix A? Okay, but I want the total amount of protein that's coming out of all the mix A that we use. See, this is telling us, okay, 2x, right? Because this is telling us the number of nutrients per unit, right? So there's 2, are these in grams? Yeah, 2 grams of protein per unit of mix A, right? So if we've got X units of mix A, the total protein coming from mix A is 2X, right? Okay, so then all this stuff right here is going to give us that combined with that need that we have. That's our nutritional need, is a total of 27. What equation is that going to give us? Yeah, okay. 2x plus 6y, that's the number of units of mix B, plus 9z equals 27. Grams of protein from mix A plus grams of protein from mix B plus grams of protein from mix C has to equal 27. Give me 1 to 5 on that. How are we doing on that? Okay. What am I going to get for my second equation? Where's that coming from? fat. Okay, that's telling me how many grams per unit of fat for each mix. I need a total of 18 grams of fat. So what's that give me then? Equals 18. Okay, and now we probably see where we're going with this. So we need a total of then also 36 grams of carbs, and this is telling us the number of grams per unit. So our third equation is going to be what? Y plus 14z equals 36. Go. What's that give us? If I throw that in a matrix. Okay, so x is 3 units. So 3 units of A. 2 units? 2 units of B and 1 unit of C. Okay, make sense? And I'm just going to put this into a, what would the dimensions be of my augmented matrix here? What's it going to be? 3 by 4, yeah. Okay. And it's in standard form, so we're good. All right. Okay, how about this one? A little engineering application. We're ramping it up a little bit. This is even a little tougher. You want to go to the boards and work on this one a little bit? I'm going to give you a little time. Jump to the boards real quick and at least see if you can come up with a strategy. You don't have to solve the whole thing, but see if you can come up with equations and variables and all that.